So previous class we end here, define the Ohm's law, derivation of Ohm's law. Here the final expression is V equal to IR, and the potential difference, current, and R is the resistance. And today we elaborate resistance and R and the factor depending on resistance. So R is the resistance, that is equal to rho L upon A, and rho is the resistivity, and you know that rho is a resistivity, that is a material property, that is a material property. Okay, so that and R is directly proportional to rho, but R from Ohm's law is inversely proportional to I. Means more resistivity means more resistance. If more resistance means less current. So here compare the resistivity of copper, metal, and resistivity of suppose wood, non-metal. So ratio of copper is a good conductor of electricity and the wood is a bad conductor of electricity. So resistivity of copper, suppose here you know that current passes through the copper is much greater than current passes through the wood. Okay, if more current is less resistance, means the resistivity of copper is lesser than resistivity of wood. Okay, that's a very important factor. So metal have low resistivity. So metal, we find metal have low resistivity. Okay, and inverse of the resistivity 1 by rho, we get conductivity. Okay, so conductivity. Okay, so previous class we discussed the conductivity here. There's the conductivity. Okay, so conductivity, this is inverse of resistivity. So conductivity is that like here you see that R equal to L by sigma A. So R is 1 over sigma, R proportional to 1 over sigma, means the inverse is proportional of sigma. So mean more resistance is less conductivity. Okay, so the conductivity of copper is greater than conductivity of wood. Okay, now here the SI unit of resistivity, we know that from here that SI unit of resistivity, that is rho, that is equal to RA by L, and R is the ohms. We know that area, cross section area is a meter square, and length is meter, that is ohm meter. Ohm meter. Similar the conductivity, that is of inverse of resistivity. So inverse of resistivity, that is equal to 1 over ohm meter. So inverse of ohm is mho, that is the ohm. So inverse of ohm is mho, MHO, mho. That is a symbol of mho. And the 1 by meter means meter to the power minus 1. Okay, that is the conductivity. Is a mho. Clear? And if there is a conductor, means a wire. Okay, there is a depending on the factor, that is a cross section area A, and that is the length, L, length of conductor, and the material, which type of material you choose, the copper, iron, or anything like that. That's depending on the rho or sigma. That's the material property. Okay, so clear the concept. So R equal to rho L by A. So R is inversely proportional of A. If more cross section area, okay, if more cross section area is R is also inversely proportional of 1 by I. So A directly proportional to I. So more cross section area means more current. If I choose a thicker material like a thicker wire, okay, so means a more current passes through that. Okay, thicker wire gets more current. That's why when I use a current or AC connection, we choose a thicker wire, because thicker wire drive the more current than normal wire. Clear? Now we discussed another concept, current density. Previous class we discussed current density. Current density, that's the vector quantity J represent the current density. The current density, and we find the expression previous class from I equal to sigma AE, we get from there, from the I equal to sigma A times E. The current density defines the current per unit area. So that is I by A, we get sigma times E. So finally J equal to get sigma E. Vector, electric field is a vector. And the sigma equal to 1 by rho. So J equal to 1 by rho times E. Okay. So finally we get rho J, vectorically rho J, that is equal to E. Okay, that's the expression of current density. Okay, box that expression, that's a very important in numerical solving or board exam. Okay, that's the current density. Okay, clear what is the current density and expression of current density, and that's conductivity and the resistivity are the constant. Okay, now clear. So now we describe Ohm's law. So previous class we discussed V directly proportional to I. V directly proportional to I. If I choose a conductor here, the potential difference is a plus potential, means a higher potential, there's a lower potential. So if I choose a free charge carrier with the electron, move from lower potential to higher potential, and the applied electric field, that is direction plus to minus direction electric field. Okay, so that's why the current direction, that is opposite of free charge carrier, if free charge carrier be the minus or the similar direction of E. Okay, so I move from plus to minus direction. Correct. So that is equal to V equal to I, and there is some constant R, resistance. So R equal to V by I. Okay. Now if I plot that expression, okay, and calculate the R, resistance, graphical representation, that's a graphical representation. If I choose R, so that's that I minus I plus V, that is the minus V. So that is a simple expression is Y equal to mx, that is straight line expression. Okay, and that is equal to m equal to y by x, and its expression look like this. Straight line. Okay, and if you choose very small amount of potential difference, suppose choose a point, these 2 points, that's a delta V1, that's the delta V1, and that is delta I1. So here delta V1 by delta I1, here we get R, and if you choose the same here, suppose here we choose another triangle, that's a delta V2, that's the delta V2, that's length is delta V2, and that is this line represents delta I2, and choose the R that is equal to delta V2 by delta I2. These two are the same. Okay, because it's a linearity property. Ohm's law satisfies the linear property. So Ohm's law satisfied linearity. Okay, means more potential difference. Okay, if you choose a more potential, means a more potential difference here, then more free charge carrier move from this direction to that direction. If I choose that electron, more free charge. If more charge, that is I equal to Q by T, more charge means more current. Okay, so that's the difference. Okay, the even more potential difference. Okay, to the more potential difference. Okay, so more free electron or free charge charge carrier move from one end to conductor to other end of conductor. So that's the Q, and we know that Q is more, so I also be the more. So that's why, so V and directly proportional to I. That's a linear property. If less potential difference means less charge carrier move, I say less charge carrier move from one end to other end. So less current means less current with a less potential. There's a linear property. Okay. And Ohm's law always the directional property doesn't depend on direction. Okay. So Ohm's law, resistance is a scalar quantity, so it doesn't depend on any direction. If you choose a plus here or minus here potential, that's why be the same R value. Okay. R is a doesn't depend. R have not polarity. Resistance have not polarity. So definition of Ohm's law, if you state the Ohm's law, if you want to write that, please pause the video and write that definition. Otherwise, your books have the definition. Okay. So Ohm's law states that the current through a device, current through a device, and the device is the resistance. Resistor. The device is resistor, and it look like this. The device, the resistor, is always directly proportional. Is proportional to the potential difference of the applied device. To the applied device. Okay, and that device, another name is called passive device. This device is named as passive device. Those devices who obey the Ohm's law, and another kind of device they do not follow the linearity property, like a PN junction, semiconductor device. Actually, if I plot a graph here, plot graph, and that's the resistance graph, and now that's the semiconductor device. Okay, that's a semiconductor device. Black color represents the PN junction, and that is I and that is V. Here you see that diagram. Okay, here the blue line represents the linearity, but black line represents the non-linearity. Means that point, choose that point where the voltage change, the potential difference change, but no current. Okay, So here BC voltage change, but there is a no current here. And if I cross this potential, suppose in silicon that is equal to 0.7 volt, and after crossing the 0.7 volt there is a huge current, very small amount of change in potential, but current value is very high. Okay, current value is very high. So that's why this device is a non-linear device, a semiconductor device, and the resistance is a dynamic resistance. These resistance are dynamic resistance. Dynamic resistance. That means change the resistance value from here, here. Okay, here the resistance is very low. Here the resistance is very high because the current is very small. Small change in current here. That's the resistance very high. Here the current change is very high. Potential with a very small. So that's why here that R is low. Here the R is high. That's why these type of resistance, the semiconductor device have a resistance. This resistance is called a dynamic resistance. Okay, clear? Now here we describe microscopic view of Ohm's law. Ohm's law. Micron is very small. Okay, if I choose a conductor, a wire, there's a wire. Before they applied a electric field or potential, and you choose there is a free charge carrier, and that free charge carrier move randomly. Okay, and without applied electric move randomly. Okay, and there's a velocity here. These velocity move randomly. You know that is a Brownian motion. You move randomly, haphazardly. Okay, move randomly, and this speed is called effective speed. Effective speed, V effective, that is approximation of copper in copper material, that is given 1.6 into 10 to the power 6 meter per second. That's a very high, the effective speed. Okay, and now you applied a electric field. Now here is a potential, that is a plus V, that is a minus V. Now we apply the potential and here the electric field in that direction. Okay, now if you choose the free charge carrier with a electron, negative charge of electron. Okay, now there the random motion slightly drift. This random motion is slightly, okay, drift. Okay, slightly drift and slowly opposite side of E, and slowly opposite side of E, slowly opposite side of E, and you see that drift, that is equal to copper, that is 5 into 10 to the power minus 7, 10 to the power minus 7 meter per second. And you see that drift speed is very less than effective speed, actually very slow. And drift speed is referred to the average speed. Drift speed is referred to the average speed. Okay, and which the electron move along a conductor. These are electron move along in the conductor. When you apply electric field, movements are superimposed. Movement are superimposed on the random thermal motion of electron. And you see that the drift is very slow. The drift is very slow. Next question, why is said drift is very slow and why effective is very fast? Because the effective has no electric field. Here there no electric field, no external electric field. Okay, but in drift there is an electric field. Okay, when the atom in a conductor and the free electron are collide each other. Okay, and the atom conductor are applied electric field. They are the colliding with, if the colliding in drift electron, why drift is slow? Why drift is slow? Important. Electron are constantly colliding, are constantly colliding with the atom of a conductor. Atom of conductor, and due to the applied electric field, when due to here present in electric field, in applied electric field, the movement are superimposed and random thermal motion of the electron, the movement are superimposed, so that's why the drift is slower than effective. Okay, the movement is superimposed, so the is superimposed. That's why the drift is very slow. And okay, and if you calculate the drift speed from previous class, the conductor, now electric field, there is a current direction same as electric field direction, and J we know that N E V D, you know that expression, okay, in previous class, and that is V D equal to J by N E. That's the equation number 1. And here when electron are moved, so there is acceleration from Newton's second law, so that is equal to force. That force is electrostatic force by mass of electron. Okay, and if a electrostatic force, and there is obviously there is a electric field, so there is a E times the, okay, the test charge or charge carrier times electric field, E times E, we know that from first chapter, by ME. Okay, and Vd, drift velocity, that is equal to acceleration times tau. And what is a tau? Okay, tau is the relaxation time. Okay, time taken between two successive collision, or average time taken between two collision. Average time taken between two collision, two successive collision actually. So that is now Vd, and replaced by A, so we get Vd equal to E times E by ME times tau. That's the equation number 2. 1 equal to 2, and we get, if 1 equal to 2, and we get J by NE and E times E by ME times tau. And here see that E, okay, E equal to, there is a J, that is ME, that's a J here. Mainly the electric field is a vector, J with a vector, other term with a constant. So ME by N E square tau, and this is a constant term. And we know that, you know, from today's class, E equal to dash some constant times J, and here we see that today's class E equal to rho J, equal to rho J. Now this is a rho, that is, question is rho equal to ME times NE square tau, and 1 by rho, that is sigma, that is equal to NE square tau by ME. Okay, There is some expression we find from previous class, and we just recall that. Now another and last topic we will discuss the mobility. Mobility is a quantity. Mobility is a quantity. Now we discuss the mobility. The very important. Okay, and mobility is that's an important quantity actually. That mobility mu, that is equal to Vd, drift velocity, by electric field. Okay, actually mobility means come from mobile charge carrier. So mobile charge carrier, they're like an electron from move from one end to other end of a conductor, like a skid. Okay, there's a mobile charge carrier, skidding. The mobile charge carrier here is a free electron. So now mobile charge carrier you choose, that is a free electron, move from one end of conductor to other end of conductor. That is Vd by E, and that is Vd equal to, we find here, that is EE by me times tau. EE by me times tau, 1 by E, cancel these two, and final expression is E tau by me. That's the mobility expression, that is a mu, important factor. And the SI unit, very important. So the SI unit is suppose we see that SI unit, that is a Vd by E. Okay, and Vd, so Vd drift velocity, that is a meter per second, and electric field E times L, that is equal to potential. That's capital V represent the potential, and the small v represent the drift velocity. So E equal to V by L, so volt by meter. Okay, so meter, so now meter square, this meter goes to up, that is volt times seconds. That's the SI unit of mobility. Okay, so mobility is a quantity. Okay, that's very important. And depending on mobile charge carrier, if you choose a mobile charge carrier electron, or otherwise the proton. Electron is the negative and proton is the positive. Okay, so today we discuss some basic mobility, current density, Ohm's law, microscopic views of Ohm's law, and what is current density, resistivity, conductivity. That's the basic. Okay, we discuss in current electricity. Next class we discuss potential difference or electromotive force, what is the factor of resistor, and the importance of resistor and resistance. What is that? That discussion we'll discuss in next class. So today in the class here. Thank you.